Welcome to this comprehensive guide on the sum rule for limits. I'm excited to share with you one of the most fundamental and useful tools in calculus that will make your limit calculations much simpler and more efficient. Before we dive into the sum rule, let's quickly review what limits are. A limit describes the value that a function approaches as the input gets closer and closer to a specific point. We write this using special mathematical notation. Now here's where the sum rule comes in. The sum rule for limits states that when you have the sum of two functions, you can find the limit of that sum by simply adding the individual limits of each function. This is incredibly powerful because it breaks down complex problems into simpler parts. The sum rule is incredibly useful for several reasons. First, it simplifies complex limit calculations by allowing us to work with simpler functions separately. Second, it breaks down challenging problems into manageable pieces. Third, it forms the foundation for understanding other important limit laws. And finally, mastering this rule is essential for success with derivatives and integrals later in calculus. In this comprehensive video, you'll master the sum rule through 6 key areas. We'll start with the formal definition and mathematical foundation. Then we'll build intuitive understanding of why the rule works. We'll work through detailed examples with polynomials and trigonometric functions. We'll also explore common mistakes and situations where the rule doesn't apply. Finally, we'll look at advanced applications and real-world connections that show the power of this fundamental concept. By the end of this video, you'll have complete confidence using the sum rule for limits in any situation. You'll understand not just how to apply it, but why it works and when to use it. Ready to master this essential calculus tool? Let's begin with the formal definition and build your understanding step by step. Now that we understand what limits are, we can explore one of the most fundamental rules for working with them, the sum rule for limits. The sum rule states that if we have two functions, f of x and g of x, and both of their limits exist as x approaches some value a, then we can find the limit of their sum in a very straightforward way. The rule tells us that the limit of the sum equals the sum of the limits. In other words, we can evaluate each limit separately and then add the results together. Let's break this down step by step. First, we need the limit of our first function, f of x, as x approaches a. This limit equals some value L. Second, we need the limit of our second function, g of x, as x approaches the same value a. This limit equals some value m. When both of these individual limits exist, the sum rule tells us we can simply add them together. The result is that the limit of f of x plus g of x equals L plus m. We've transformed a potentially complex limit problem into simple addition. However, there's a crucial condition we must always check before applying the sum rule. Both individual limits must exist and be finite. If either limit doesn't exist, or if either limit is infinite, then we cannot use the sum rule. To summarize in simple terms, if you can find the limit of each function separately, you can just add those limits together to find the limit of the combined function. This visual representation shows exactly how the sum rule works. We take the limit of the first function, add it to the limit of the second function, and that gives us the limit of their sum. This rule makes evaluating limits much easier because it breaks down complex expressions into simpler parts that we can handle individually. To truly understand the sum rule for limits, we need to go beyond just memorizing the formula. We need to understand why it makes intuitive sense. The key is understanding what a limit actually means. When we write the limit of f of x as x approaches a equals L, we mean something very specific. As x gets closer and closer to the value a, the function f of x gets closer and closer to the value L. Let me show you this concept visually. Imagine we have a function f of x, and we want to find its limit as x approaches the value 2. Here we have a function f of x. Notice that as x approaches 2 from either side, the function values approach the value 2. This is what we mean by the limit equals 2. Now let's consider two functions. Suppose we have f of x approaching L as x approaches a, and g of x approaching m as x approaches a. Here's f of x in orange approaching the value 1.5, and here's g of x in green approaching the value 1. As x approaches 2, f of x approaches 1.5, and g of x approaches 1. Now, what happens when we add these two functions together? If f of x is approaching 1.5 and g of x is approaching 1, then their sum should approach 1.5 plus 1, which equals 2.5. And indeed, when we graph f of x plus g of x, we see that it approaches exactly 2.5 as x approaches 2. This is the sum rule in action. The sum rule works because it reflects the natural, intuitive behavior of limits. If one function is approaching a certain value and another function is approaching a different value, then their sum naturally approaches the sum of those values. Think of it this way. If f of x approaches L and g of x approaches m, then f of x plus g of x must approach L plus m. This is the essence of the sum rule. It's not just a formula to memorize, but a natural consequence of how limits behave. Understanding this intuition is crucial because it helps you see that the sum rule isn't arbitrary. It's a logical extension of what limits mean. This foundation will help you understand not just how to use the sum rule, but why it works. Now we'll work through our first example to see the sum rule in action. This will demonstrate how breaking down a complex limit into simpler parts makes the calculation much more manageable. Here's our problem. We need to find the limit as x approaches 2 of the polynomial 3x squared plus 2x minus 1. This is a polynomial function, which makes it perfect for demonstrating the sum rule. Notice that our function is the sum of three terms, 3x squared plus 2x plus negative 1. Now we apply the sum rule. This allows us to break our single complex limit into three separate simpler limits. The limit of the sum equals the sum of the limits. Now we'll evaluate each of these three limits one by one. This step-by-step approach makes the calculation much clearer and reduces the chance of errors. Step 1. We evaluate the limit of 3x squared as x approaches 2. Since this is a polynomial, we can substitute directly. 3 times 2 squared equals 3 times 4, which equals 12. Excellent. Our first limit equals 12. Now let's move on to the second limit. Step 2. We evaluate the limit of 2x as x approaches 2. Again, we substitute directly. 2 times 2 equals 4. Great. Our second limit equals 4. Now for the third and final limit. Step 3. We evaluate the limit of negative 1 as x approaches 2. Since negative 1 is a constant, it doesn't depend on x, so the limit is simply negative 1. Perfect. Now we have all three individual limits. Let's combine them to get our final answer. Now we add our three results together, 12 plus 4 plus negative 1. This gives us 12 plus 4 minus 1, which equals 15. Therefore, the limit as x approaches 2 of 3x squared plus 2x minus 1 equals 15. This is our final answer. The key insight here is that the sum rule transformed one complex limit into three simple limits. Instead of working with the entire polynomial at once, we handled each term separately, making the calculation much more manageable and less prone to errors. This demonstrates the power of the sum rule for polynomial functions. In our next example, we'll see how it works with trigonometric functions. Now let's explore how the sum rule works with trigonometric functions. This example will demonstrate that the sum rule isn't limited to polynomials. It applies to any functions where the individual limits exist. Here's our problem. We need to find the limit as x approaches 0 of sine x plus cosine x. This involves two different trigonometric functions combined in a sum. Step 1. We apply the sum rule for limits. Since we have a sum of two functions, we can split this into the sum of two separate limits. The limit of sine x plus cosine x equals the limit of sine x plus the limit of cosine x. Step 2. We evaluate each limit separately. The first limit is the limit of sine x as x approaches 0, which equals 0. This is a fundamental trigonometric limit that you should memorize. The second limit is the limit of cosine x as x approaches 0, which equals 1. This is because cosine is continuous at x equals 0, and cosine of 0 is 1. Step 3. We add the results together. 0 plus 1 equals 1. Therefore, the limit of sine x plus cosine x as x approaches 0 is equal to 1. Here's the key insight. The sum rule works for any type of functions, not just polynomials. Whether you're dealing with trigonometric functions, exponential functions, or logarithmic functions, as long as the individual limits exist, you can apply the sum rule. However, remember this crucial requirement. Both individual limits must exist for the sum rule to apply. If either limit doesn't exist, then we cannot use the sum rule to evaluate the limit of the sum. To summarize our complete solution, we started with the limit of sine x plus cosine x as x approaches 0. We applied the sum rule to split this into two separate limits. We evaluated each limit individually, getting 0 and 1 respectively. Finally, we added these results to get our final answer of 1. Now we need to discuss a critical limitation of the sum rule. The sum rule is a powerful tool, but it comes with important conditions that must be met before we can use it. Remember, the sum rule states that the limit of a sum equals the sum of the limits. But this rule only works under specific conditions. The key condition is that both individual limits must exist and be finite. If either limit of f of x or limit of g of x does not exist, then we cannot apply the sum rule. Consider this example. The limit as x approaches 0 of 1 over x plus 1 over x squared. A common mistake would be to try applying the sum rule directly. The incorrect approach would be to split this into the limit of 1 over x plus the limit of 1 over x squared. But this is wrong because we're violating the key condition. Here's why this fails. The limit of 1 over x as x approaches 0 does not exist because the function approaches positive infinity from the right and negative infinity from the left. Similarly, the limit of 1 over x squared does not exist because it approaches positive infinity from both sides. The correct approach is to combine the fractions first. We rewrite 1 over x as x over x squared, then add the fractions to get x plus 1 over x squared. Now we evaluate the limit of x plus 1 over x squared as x approaches 0. Since the numerator approaches 1 and the denominator approaches 0, this limit still does not exist. It approaches positive infinity. Here's another example. The limit as x approaches 0 of x squared plus 1 over x. In this case, one limit exists, but the other doesn't. Let's analyze each limit separately. The limit of x squared as x approaches 0 equals 0. This limit exists. However, the limit of 1 over x as x approaches 0 does not exist because it approaches positive infinity from the right and negative infinity from the left. Since one of the individual limits doesn't exist, we cannot apply the sum rule. Therefore, the limit of the entire expression does not exist. Here are the key takeaways. First, always check if individual limits exist before applying the sum rule. Second, if either limit doesn't exist, the sum rule fails. Third, when the sum rule doesn't apply, use alternative methods such as combining fractions algebraically, factoring and simplifying expressions, or using L'Hopital's rule when applicable. Remember this important warning. Prerequisites must always be met before applying any limit rule. The sum rule is powerful, but only when used correctly under the right conditions. Now that we understand the basic sum rule for two functions, we can explore its powerful extensions and see how it connects to other fundamental limit laws. The sum rule can be extended beyond just two functions. If we have three functions, f, g, and h, and each has a limit at point A, then the limit of their sum equals the sum of their individual limits. This pattern continues for any finite number of functions. We can write the general formula for n functions, where each function has a limit at point A. This is incredibly powerful because it means we can break down complex expressions into simpler parts. For example, if we have a polynomial with many terms, we can find the limit of each term separately and then add them together. The sum rule is part of a comprehensive family of limit laws. These include the product rule, which handles multiplication of functions, the quotient rule for division, and the constant multiple rule for scaling functions. These rules work together seamlessly. When you encounter a complex limit problem, you can often combine multiple rules to solve it step by step. The key is recognizing which rule applies to each part of your expression. The beauty of these limit laws is that they transform complex problems into manageable pieces. Each rule handles a specific operation, and together they provide a systematic approach to evaluating limits of virtually any elementary function. Remember, the fundamental requirement for all these rules is that the individual limits must exist and be finite. When this condition is met, these limit laws become powerful tools that simplify even the most complex limit calculations. We've reached the end of our exploration of the sum rule for limits. This fundamental concept in calculus is one of the most important tools you'll use when working with limits. Remember, the sum rule states that the limit of a sum equals the sum of the limits, but only when both individual limits exist and are finite. Here are the key takeaways you should remember from this lesson. First, and most importantly, always check that the individual limits exist before applying the sum rule. Second, we've seen that this rule works beautifully with polynomials, trigonometric functions, and many other types of functions you'll encounter in calculus. Third, remember that if either individual limit doesn't exist, then the sum rule simply cannot be applied. This is a crucial condition that students often forget. Fourth, the sum rule extends beyond just two functions. You can apply it to finite sums of multiple functions, making it incredibly versatile. Finally, remember that the sum rule is part of a larger family of limit laws, including the product rule and quotient rule, which follow similar logical patterns. Congratulations! You've successfully learned the sum rule for limits. With this powerful tool in your mathematical toolkit, you're now ready to tackle more complex limit problems with confidence. If you found this explanation helpful, please give this video a thumbs up. It really helps other students discover these tutorials. And if you have any questions about the sum rule or limits in general, drop them in the comments below. Don't forget to subscribe and hit the notification bell for more calculus tutorials. Coming up next, we'll explore the product rule and quotient rule for limits, which build on everything you've learned today. Thank you for watching, and remember, mathematics is a journey of discovery. Each concept you master opens the door to understanding even more fascinating ideas. Keep practicing, stay curious, and I'll see you in the next video.